Okay, I'm going to go over a couple of problems from the review that I had a student ask about and post them for anybody who would like to listen along. It's about 6 problems off of the exam 2 review. So the first one that's asked about is this one, number 9. This is use the square root method to solve the quadratic equation. So the first thing that I want to comment on is on the test, as long as you can solve the quadratic exactly, I don't really care that much whether or not you can use this particular method or not, but it is a little faster. So let me go ahead and show you what we're doing. I'm going to stop sharing that so that I can, share the camera here and show you what I'm talking about. All right, so this is a quadratic equation that's missing the x term in the middle. So the only place it has the variable term in it is this quadratic term. So we can basically solve this thing where it says x squared equals something and then just take a square root to finish solving it rather than assigning the middle term to be 0 for b and working out quadratic formula or factoring. So what we'll do here is we're going to get the x squared by itself. So that means I'm going to add the 49 to both sides. And so the 0 plus 49 give us 4x squared equals 49. Then I would like to divide both sides by 4 because I'm trying to get this part by itself. So now I have x squared equals this fraction. I'm just going to leave it an improper fraction, 49 fourths, because the last step when you have x squared and you want to get back to x is the inverse of squaring is to take a square root. You want to be careful here though, because, ignore that, x to the first. Once you take the square root of x squared, that just becomes plain old x. And then when you take the square root of a fraction, you do the numerator and denominator separately, which of course is 7 and 2. But there are always 2 square roots to a number, the positive and the negative version. So right here, there's going to be a positive and negative square root of 49 fourths for an answer. So your final answer will be both positive and negative 7/2. So that also could be done with factoring, which would produce 2 factors, which would produce 2 solutions. Or you could run it with the quadratic formula, which because of the plus and minus, the square root of b squared minus 4ac in the quadratic formula would also produce 2 answers. But when they say by doing square roots or taking the square root extraction, it means solving for the variable squared and then just taking a square root on the last, or to get rid of the squared. And then if there's anything else under the square root with the variable, then you would continue to work until it's completely solved. So that's how we would do number 9 would be, we would get the squared variable by itself, take a square root on both sides, and remember to include both the positive and negative square root for your final answer. All right, so that was number 9 on the review on the particular problems that I have. Now, as you guys all know, everybody gets different numbers in their problems when they're working on it. This is just the one that I got. So the next one to look at is number 11. So let me go and get that one pulled up and then show it to you. Okay, so what this one is saying, let me show you what it looks like, and then we'll move to another screen to solve it. Let me find it. Where is it? Right there. All right, so this is number 11. It's again with solving quadratics. It says find the exact solutions. So that usually means we're going to work something out by hand and we're going to calculate the perfect answers either with factoring or the quadratic formula or taking square roots like what we just did here. But it does say in the complex number system. So that means it's a possibility that when we compute the answers, we might get something like the square root of a negative number that might have an imaginary piece. We just won't know until we work it out, but we're going to get the exact solutions no matter what kind of answers they are. It does tell us, it says confirm that the solutions are not real. So if they're not real, that means they have an imaginary piece to it. It says confirm that the solutions are not real by showing that the graph does not cross the x-axis. Okay, so we'll worry about that part of the problem in a minute. Let me first copy this problem down so we can kind of carefully work out the 2 solutions. Okay, and then we'll talk about how solutions to a quadratic, what that tells you about the graph of a function here in a minute. So let me now go and put it onto my paper. All right. So to find an exact value, there's some techniques that work sometimes, but what always works is this. The quadratic formula will always calculate the exact values of any quadratic as long as it's in standard form where all the terms are on one side equals 0. It must be 0. So the a and the b and the c are the coefficients here, descending powers of x. So a is going to be 1, b is going to be 8, c is going to be 25, and then we're just going to plug and check. So x equals, so negative b, be negative 8, plus or minus, b squared, 8. I always put the b in parentheses in case it's also negative. I want to make sure I don't miscalculate the sign there. 4 times a, which is 1, times c, which is 25. And all of this is divided by 2a, which will just be 2 times 1, which is just 1, or 2, of course. Now I'm going to go ahead and just cram all this into my calculator that has disappeared, Paul Buckaloo. My calculator has disappeared. What was it here? Yeah. On the video. We'd like to in your own mind. Okay. So I'm hoping this will show up okay on camera. I wanted to show you guys a nice thing about these calculators. You can put the entire expression directly into your calculator, and when you calculate the first part of your answer, then you can just go back through and put a negative in there to do the second part. But let's do this first part actually, and I may not have to go that far because I think this stuff under the parentheses is going to end up being a negative number. So 8 squared minus 4 times 1 is 4 times, oh, I could have done that in my head, but 4 times 25 is 100. So 64 minus is negative 36. All right, I don't think I need a calculator to do the rest of this. So this part worked out to be negative 36 plus minus negative 8 all over 2. Okay, so the fact that I have a negative right under here means that when we go to simplify, the square root of negative 1 is the same thing as I. So if you have a negative radicand, you always want to bring that out, and that's the imaginary part of your answer, and then you'll leave the positive radicand underneath there. And then, of course, square root of 36 is 6. So these are my two solutions. I have negative 8 plus and minus. The square root of 36, I write it without the square root sign once I compute the square root of 36. And all of this is over 2. And since in this case, if you have a common factor between your denominator and both pieces of the complex number up here, you are allowed to reduce both of them or all 3 of them by that common factor. So these all can reduce by 2. It'd be just like if you broke it up into 2 separate fractions like this, over 2i. Negative 8 over 2 is negative 4, 6 over 2 is 3. So this actually has all quadratics, most, I shouldn't say all, have 2 separate solutions. And so if I was going to write it like they want it in my math lab, they usually want you to write them as 2 separate solutions. So one is them with the plus, and then separate it with a negative sign, and the other one's with subtracting your imaginary term. So these are my 2 solutions to this equation, negative 4 plus 3i, negative 4 minus 3i. And because of that imaginary part, that means they are complex, non-real solutions. Okay, now the rest of this problem said used a graph and the x-intercepts were used to look at the graph to verify that these are complex solutions. X-intercepts correspond to the real valued solutions. Let me write that down as any real valued solutions to the quadratic, to the setting the function equal to 0. So I'm going to have bad language here and say if we have this function f of x f of x's x-intercepts are the same value as any real valued solutions. So if it had solutions of 5 and 4, we're going to see x-intercepts at 5 and 4. This, because it has solutions that can't be graphed on the real number line because of the imaginary step, we won't be able to see any x-intercepts when we graph it. So let's see what that's going to look like. If I can find a place to put that. Okay, so let me go back up to the original function. And you can think of the original function. Actually, I'm going to switch over, just look at, rather than try to use my really reflective handheld computer, I'm just going to go to the emulator here. Okay, so the part that I had on the paper when I had my a, b, and c, x squared plus 8x plus 25 equals 0, the part that was on that left-hand side, that is what you want to think of as the function that we're referring to. So I'm going to put in that expression, x squared plus 8x plus 25. And when I graph this, what it should do is wherever the vertex is located, it'll either be located above the x-axis or below the x-axis, but the direction that the vertex, or that the parabola opens up from the vertex, is going to open up away from the x-axis. So I'm going to assume it's located somewhere above the x-axis and opening upwards. So I'm just going to put it in the standard viewing window because I don't know what the window is, and let's see if it shows up. Barely see it right there. Let me make the top of the window a lot taller so we can see it. Put it up to 20. And I'll just have it start at -1. Doesn't really matter as long as you can see where it's turning around. But you could, as we know from parabolas and quadratic graphs, that they never change direction except for that one time. That's kind of going to be like lines going up forever on both sides. So we can see that this thing is never going to have x-intercepts. It's the vertex, the lowest point is above the x-axis, and it's opening even further upward. So it will never have any way to cross the x-axis. So when you see a graph like this, it means the function that you're looking at, if you were to set that function equal to 0 and solve it, you would end up getting answers that have complex solutions like the one that we did that has the I in it. So that's something that you know from the type of solutions that you have, whether or not you're going to have any actual x-intercepts on the graph of that function. Okay, so that would help us to answer that question number 11, the actual x-intercepts. So let me go back to the problem. It probably wants us to enter something in. Let me look and see. So let me go back to that one. See what it says. All right, so the solutions are type it in the form a plus bi, use radicals, use a comma to separate. All right, so our first one was -4 plus 3i. So let's do -4 plus 3i, and then -4 minus 3i. Do I have it right? A plus bi. Let's see. Can't get out of the way. Check the answer. Good job. Oh, that's it. So on the, it didn't ask us to do anything to prove that we verified it with the graph. It just said do it. So, all right, we're done with that. Okay, so enough of that one. The next one was actually number 13. So I'm just going to stay on this screen and let's see what number 13 is. Okay, so now we're getting to an application of a quadratic, which we see these all the time where there's stuff flying through the air, being shot like rockets up in the air, balls being thrown up in the air, stuff just, you know, being dropped off of stuff. But when gravity is acting on something as it's traveling up and hitting its peak or just falling, the graph of the distance, the height it is versus the time after the thing has started to rise and fall or whatever is always a quadratic model. All right, so this is a ball that's being thrown up in the air at 96 feet per second from a height of 4 feet. And the height of the ball can be modeled by, and then there's our expression, 4 plus 96t minus 16t squared feet, where t is the number of seconds after the ball is thrown. So in this problem, they're not using x and y, they're using t for time, and then s for height. I don't know why I would probably use h for height, but they're using s. So really they should write it like a function and say s of t, but they're calling the outputs s and the inputs t. T is the number of seconds after the ball is thrown, and it says the height is measuring in feet. Okay, so the S values are in feet. So then they ask us this question, how long after the ball is thrown is the height 112 feet? Now they don't tell us how to solve this, so I'm actually maybe going to bore you and show you more than one way here, but I'm going to write down my function on my paper. I'll show you, actually I'm going to show you a graphing way first, and then I'm also going to show you a way you could calculate it even more precisely by hand. All right, so the question is, when you have a height of 112 feet, then what is the time, right? It says how long after the thing was thrown. So let me get off this. And then we'll go over to the paper just to show you what I'm setting up, and then I'm going to switch over to the computer, the calculator, sorry. All right, so if it's a height value that they give you, this is why we have to learn how to solve things, because a lot of times they give us an output and we're trying to work backwards and figure out what the input would be. So if we want to know when is it 112 feet, I'm going to write that out. I'm actually going to rearrange my terms as well so that it kind of looks more like our standard order of terms for a quadratic function. So I'm going to write the squared term first and the constant term last. So I'm just switching these first and third terms around. But I'm going to set it equal to what they told me they wanted to equal. They want it to be, remember this is calculating all kinds of different heights depending on what you plug in for T, but they're asking us when's it going to be 112? So we're going to actually put the output in there for us, equals 112. And now we need to work it backwards and figure out what this is. Okay, two good ways. One way is like what we were doing before, where we would use the quadratic formula or possibly factoring to solve it by hand. To do that, though, we would need to have a 0 over here. So if we did that, we would have to first start by moving this number over, and that would give us negative 108. We'd want to make sure and adjust our C value here to account for not just a constant C value that was in the original problem, but this output, once we bring it over and combine it, that would be our C value, negative 108. A would be negative 16, B would be 96. But they didn't say how to do this problem. So before I go further and try to do a quadratic formula, so I'm just going to say use quadratic formula. There's probably going to be a positive, well, I don't know. There might be a positive and negative. There probably will be two answers. We'll see. Anyway, we can use a quadratic formula. Or what we can do is we can use the graphing calculator. Because if I graph this, it's going to start at 4 feet here, and it's going to come up and go back down. It says at 0 seconds. I don't know how many seconds it's going to take to hit the ground, but let's say this is 112 feet high. At some point, unless it doesn't even get that high, at some point it's going to pass through 112 feet on the way up and then again on the way down. So we could look at the graph and kind of find that point. So what we're going to do, I'll switch over in a minute, but this is a way to solve by graphing. What you do is you put whatever equation you're dealing with, and let me remind you what it is. Negative 16 squared plus 96t plus 4 equals 112. That was our original equation. Just take the original function that you were dealing with and put it into your calculator like you normally would, and then you take whatever's on the other side, this works for any equation really, and put it in for y2. Now remember, on our calculators, they're not that smart that you have to change the t's to x's. So this is what I'm getting ready to do on my calculator. 4, and then y2 is going to be 112. I'm going to adjust my window to make sure the y value is up way past 112 so I can actually see where this line kind of cuts through the points. And then I'll use my intersect feature. So you graph them both, and then you use your intersect to find the x values of your intersect point. And those are going to be your solutions. So watch this. I'm going to share the calculator now, right there. Okay, so I'm going to put that left-hand side of the equation in, negative 16x squared I know it said t in the homework problem, but we have to use x's. Plus 96x plus 4. It said, remember it said it starts at a height of 4 feet. So like that's when the person let go of it or whatever with pitching it up in the air. And then that's going to give us the graph of the height versus time. And then the second one is we want to know when's it going to be 112. So I'm going to put that here. Now let me think about what I want to do here. My window, I know my y value needs to be way up higher, the y max higher than this, so that I can, that's just going to make a graph of a horizontal line across my screen. And if I did it with the settings I have right now, my y max only goes up to 20 and I won't see the part of the graph where it hits 112 because I'm not looking high enough. So I'm going to set this at like 140 maybe. Okay, so I'm going to set it at 140. And this is all just kind of trial and error, but that's a given that if you have a specific output that you're interested in and you want to use the intersect feature, be sure that your y max is set well above that number, which for us in this problem is 112. And then I don't know if I don't really need negative x values because they're measuring the time after it was thrown. So maybe I'll just start that at 0. And we'll see, surely within 10 seconds, the thing will have hit the ground. I don't really care about changing my scale. I know it, probably jam up the screen, but I just want to see what the graphs are. So let's see if 10 seconds is enough to see the whole thing. Well, it is. All right, so remember the blue graph measures how high it's going at certain seconds. So at 2 seconds, it's right here. It looks like the top of it's just out of reach here is 1, 2, 3. So around 3 or 4 seconds, or about 3 seconds, it's reaching its peak, but they're not asking about where did it get the highest height. They want to know when did it hit 112. So now everything on this red line is the second graph, and that is 112 for y. Every y value is 112. So I would like to know where this x value is, where it's crossing the blue line, what the x value of that is. So that's the first time it's going to have a height of 112. You can see it's between like 1 and 2. And then over here, as it's falling, that place where the blue line hits the red line is another place where it's at 112, and that looks like it's between 4 and 5. 2, 3, 4. All right, so let's use the intersect feature, which you should have learned already. It's one of the calculations over the trace key. So I'm going to hit second calc. I'm going to pick number 5 for intersect. And it's asking me a series of questions. Look at the top of the screen. Is the first curve y1? Because you could have a whole bunch of things graphed here. So I'm just going to hit enter for yes. Is the second curve the red one? Y2, yes. Now it wants us to do a guess because we do have 2 points. So I'll just find this one on the right here first since my cursor is real close there. Now I'm going to hit enter again, and boom, it pops out down here at the bottom. It says x equals 4.5, where those two things intersect. We know, of course, the y is 112 because everything on the red line is 112. But 4.5 is where it's also on the blue line, and that's the trajectory, not the trajectory, the height of the function. So let me write that down because we're going to find the other point too. So x equals 4.5 is one of them. Notice that it doesn't, let's check it and make sure. I'm going to hit trace and type in 4.5 just to make sure that it's exactly 112 and not just real close. See if it's exact. It is telling me that there's no decimals, anything. So 4.5, when I plug it in, it really is 112. So that works. Now I'm going to run that same feature again, but just move my cursor over here for the guess. So second count. For 5 for intersect, yes for the first curve, yes for the second curve. The guess now, I want to put it closer to the one on the left that I haven't found yet. Enter, it's telling me 1.5. So I'm going to write that down on my paper. That's the other one. I'm going to double check to make sure. So if you hit trace and it shows you y1, you can put in whatever x value you want. So I'm going to type in 1.5 just to double check. It shows exactly 112. So 1.5 and 4.5 are the exact answers for when does this function, when does this ball have a height of 112? At 1.5 seconds, and then the other one was at 4.5 seconds. Okay, so that can go quicker if you don't have to explain it every time, but if it doesn't specify how you're supposed to solve a quadratic, and especially if it's asking for decimal estimates anyway, so they're not necessarily going to be exact when you report the final answer, you can always just put in the left-hand side of your equation in y1, the right-hand side of your equation, particularly if it's just a specified output like this, in Y2. Adjust your window to make sure that your Y max is higher than the number that they're referring to, which is 112. And then when you graph them, you should see the horizontal line represents where the outputs are that number they're asking about. The other curved line or whatever that intersects it represents where the function that you're dealing with is going to have that particular output. And then when you run the intersect feature, you'll find out what exactly those X values are. Those two X values are the same X values that you would be calculating by hand using the quadratic formula, or sometimes by factoring if it's possible to factor. Okay, so I think I'm going to punt on actually showing all the algebra for solving it by hand, but I just want to remind you where what I was looking at right here. Well, not right here. What was it? It was negative t squared plus 96t plus 4, I think. If you took those, I'm not going to do it because I'm lazy. We already figured out the answer. If I took negative 16, 96, and 4 and ran it through the quadratic formula, reduced those two answers at the very bottom, these would be the two numbers I would get. Okay, so that was number 13. Let me see if they had any other questions with that. So let me go back to number 13. Where is it? Where is it? There. Nope, not there. Sorry, let me try it again. That one. Hello? Why did it not? Have I lost the internet? There it is. Use it integers and a comma separated. Integer or simplified fraction. Use comma to separate the answers. Okay, well, let's see. Simplified fraction, 1.5 would be 1.5. I guess they want 3 halves. And 4.5 would be 4.5 would be what, 9 halves? Yeah. All right. I don't know if it has more than one part to it. So let's do 3 halves. Oh, they had mixed numbers. I can do this. So I can do 1.5. And I can do 4.5, 4.5. That gives us, oh, that's all it wanted. Good. Okay, so our last three, we're going to look at 18, 24, and 27. So let me look at number 18, see what we're dealing with here. Okay, so these, it's just going to be helpful if you play around on your calculator and put these into your calculator and understand what the basic shape of these 6 functions are. These are what we call the key functions, or sometimes you hear them called the parent functions, the basic function. So you should already recognize a couple of them. Well, the x squared one, we know that anything with x squared is going to be a parabola, looks like this. So I'm just going to tell you what they are. You're just going to have to recognize these. Okay, so you need to practice until you understand. And this whole, that was from, what is it? There's just a homework section called key graphs. It's not really got a section number attached to it. And all the questions in it are just recognizing which of these things it is. So I'm just going to go by the pictures first. So anything that has a smooth turning point, these first two are kind of similar, but if it's curved as it changes direction through the origin here, notice all of them touch the origin except this one that's got the 2 separate pieces. So this one that has a curved turning point, that's a parabola. We've already been studying that. So that is x squared. So that is b. All right, the next one that's similar, only no curves, a straight line that comes down to a point and then kind of bounces in a point off the origin. It looks like a V shape. So think of the word that has absolute value in it. So V is for value. So absolute value right down here, if you were to graph it, When you plug in a negative number, it makes it positive, but if you plug in a positive number, it stays positive. That's what we see here. Negative x values have positive y values, but positive x values still have positive y values. So that's absolute value, that's f. Okay, the next one here, notice that it is only defined in this first quadrant up here. It doesn't even have any negative x values that you can use. It kind of just starts on the origin and then it takes off this way forever. I know it doesn't have a little arrow forever, but it's supposed to go forever. So when you look at these functions, when you have a square root, we just talked about this with the quadratics earlier, we can't calculate the square root of a negative number and have it show up on this graph. So when you're dealing with square roots, there are certain parts of the domain that you can't use. Like it has usually a starting number for x and then it goes on up or on down from that starting number. That's what this is. So that is what a square root function looks like. You also might think it kind of looks like half of a parabola tipped over on its side. And that's because squaring and square rooting are kind of related functions. They're sort of inverse functions. And so they have similar looking graphs. It's just that if you tip this over on its side, if you have a sideways parabola, it doesn't fit the definition of a function unless you chop it in half. So it's just the top half of the parabola. That's the square root. Okay, now you can see that these bottom three across the bottom, the first and the third one have similar shapes, but again, one's just kind of tipped over on its side. So those probably have a relationship between the calculations. So if you look at the ones we have left, we have x cubed, 1 over x, and cube root of x, so we haven't used yet. So you might spot they both involve this 3x cubed and cube root. Those are functions that sort of are inverses or opposite steps that undo one another, so their graphs are going to be similar looking. So x cubed is the one that looks kind of like the one above it, a parabola just kind of unhinged on one side and fell. So that's what x cubed looks like. So we're going to put a there. And I'm going to skip over here and say if you kind of flip it over and tip it on its side and where it's more strung out horizontally, that's what the cube root looks like. Okay, they all still go through the origin, all of these other ones. So the S kind of S looking shapes, the more vertical one is a cube and the ones stretched out sideways are a cube root. And then the only one that doesn't fit that doesn't hit the origin in any way is this odd one that has two separate pieces and then there's just nothing going on the X or the Y axis. It doesn't have any intercepts at all. That is the reciprocal function or the 1 over x function. Okay, so it doesn't have any definitions. There is no defined value for x. That means there's no y-intercept because if you plug in x to be 0, it's undefined. You can't divide by 0. So that's why you can't, there's nothing on the y-axis because you can't have x be 0. Same thing for the y-axis. Or for the x-axis means where y is 0. Well, a fraction can't be 0 unless the numerator is 0, and the numerator is not 0. So you're not ever going to have it hit the x-axis because you can't have an output or a y value be 0 in this particular function. Anyway, so if you know what these basic shapes look like, then it's easier for you to recognize. And for example, if the square root function has been kind of scooted up 1 and moved over to the right 3, so the v shape's over here now, you at least know what basic calculation you're dealing with because you recognize the shape of the graph. So it just makes it a lot faster if you know how to do these without having to plug every graph of every single thing into your calculator. So if you don't know these already, you're expected to be able to recognize these basic shapes on site without having to graph them. Or if you see a function that involves, say, a square root of a whole bunch of expressions that have an x in there somewhere, you're expected to know that the graph will be some variation on, I heard a professor call this the eyebrow graph. I kind of like it because it kind of does look like an eyebrow. But the eyebrow graph would be what you get if you're graphing something that has an x under a square root, even if it's got other stuff with it. All right, so that's just basically recognizing those graphs. So I'll stay on this one and let's look at the next one's number 24, and then we'll be about done. 24. Okay, so this is symmetry, and this is kind of a very visual, easy thing to think about. I'll bump it out and make it bigger so we can look at it a little more. Okay, it wants to know what kind of symmetry this has, and there's 3 specific kinds we're talking about: x-axis symmetry, y-axis symmetry, or neither. And sometimes it can be more than one. There's also one called origin symmetry, but it's not really asking about that here. All right, so just for x-axis and y-axis symmetry, I'm just going to explain it visually. I know that if you kind of Google it and look it up online, there's very algebraic definitions that talk about plugging negative x into the function and seeing what happens when it comes out, but they don't really give us an expression, they just have a graph. So symmetric about the x-axis means you see the same reflection above and below the x-axis. So that means if this were on a piece of paper and I were to take and fold that piece of paper along the x-axis, every piece of the graph that's above the x-axis would have a matching piece down here that it would match up with. And everything that's below the x-axis, when you fold it together, would have a matching piece on top of it. We do not have that here. If I take and fold this along the x-axis, let's say, see this far left piece that has a turning point here? If I were to fold that, this piece up here would land down here, and there's nothing down here to map it to. So the symmetry means you see the same exact mirror image above and below the x-axis, which we do not see. But if you flip your brain the other way and say, well, what if we folded it along the y-axis? Would it kind of split it right down the middle? And that you can see does, because look at where these two x-intercepts went. There's one just a little bit past -1 over here. If I were to fold this piece over to the right, this x-intercept would be right there where there's a little x-intercept just past 1 on the right. Same thing with that turning point I was talking about below over here on the left. There's nothing, this is up here in the second quadrant. If I fold it like from the left to the right, like this point will end up landing on top of this one. So this shape right here is the mirror image for that piece. And the same thing with these two pieces that are kind of hanging down here. If I fold them together, this piece, this loop down here matches this. This curve, kind of like, think about like a little parabola thing in the middle, is split right down the middle. So the left part will match the right part. So this one is symmetric if you fold it across the y-axis. Not so much if you fold it up and down, but if you fold it left and right, you will have matching pieces to kind of connect on both sides. So this particular graph has symmetry about the y-axis only. Some graphs you have don't have any kind of symmetries, but this one actually does have the y-axis symmetry. All right, so let's look at the last one. Number 27. Okay, so this is about combining all these functions, and this is the section that everybody tries to take the test without doing the last piece of homework, and then they just guess through this, and it's gonna, you'll pay for that. All right, so let me look at these. We have these two separate functions, and there's different ways to combine functions. But I think it was just maybe the last part about the domain that this particular student was asking about when I went and looked. So I'll go ahead and write this down, and then this will be our final problem. X plus 1. The first part is to add them. That doesn't really matter what order you write it in. The second one is to subtract them. That one, the order does matter. The third one is to multiply them. Again, order not important. The last one is to divide. Order is important. And then part E was to state the domain of that last one. Okay, so let me switch over to my paper so we can finish this up. Okay. All right, here we go. All right, so this combination, this is just kind of a way to kind of a shorthand notation, because math people are lazy. We don't like writing stuff out over and over. So rather than writing out the parentheses all the time, we just write the names of the functions and what we want to do with them. So in part A, it says f plus g of x. It means just what you think it is. It's add this expression to that expression. So f plus g of x will just be the first expression, x squared plus 2, plus the second expression, 2x plus 1. That's f of x, that's g of x. If you happen to have any like terms, we do want you to go ahead and simplify them. So since they both have a constant term, plus 2 and plus 1, I can combine those two little terms and call it plus 3. So it saves us one tiny step. We just have to add one constant instead of two separate constants. So that's what f plus g of x, just combining them together into one function, would look like this. Okay, now pay attention on the homework or on the test or whatever, whether it says x here or whether it has a number. Because this isn't on this particular problem, but I always feel like I have to comment. Let's say it had, I don't know, 5 here. If you have a specific number here instead of x, okay, the x means we just want the general expression. So just put the two expressions together the way it says to, simplify that, and you have a new expression in x. If it has a specific number, it also means you could just take 5 and plug it into each expression separately, then add the answers, or you could combine it first and then plug it in. But pay attention to what is between the parentheses, not just the operating symbol, but whether you have an x here or whether you have a number here. If you have an x here, it's just going to be a new expression with x in it. If you have a number here, you're going to have a numbered answer. That'd be what, 25, 35, 38. Okay, so make sure you look and see what's here and don't just automatically always do it for the general case of x if it's asking for a specific thing. Anyway, I won't do that for all of them. The next one is f minus g. So it's just what we said before. The first expression is f plus 2 minus. Be careful when you subtract. If it has more than one term, put that second expression in parentheses because you want to distribute that negative before you try to combine like terms. Minus 2x minus 1. And then let's put our terms together. Minus 2x, and then we have 2 minus 1 is 1. So that would be when you subtract them. The third one, now we're going to multiply them. Just what we think. We have x squared plus 2 times 2x plus 1. I don't know if it asks us to simplify this or not. Usually it does. So on something like this, we're going to have to actually multiply it out. So it's kind of like some people call it the FOIL method. We'll take this term times each one of these, and then the second term times. There'll be 4 terms. So I'm going to do x squared times 2x, 2x cubed, x squared times 1, x squared. Then I'm going to take the 2. 2 times 2x is 4x. 2 times 1, 2. There are no like terms, so that's it. So it's either these two factors. If it doesn't say simplify, you can probably get away with that. If it does say simplify, you're going to have to FOIL it out and then see if there's any like terms. All right, the last one is easy compared to the other ones. When it just says f over g or f divided by g of x, it really just means set up that fraction. So f was, what was it, x squared plus 2 over g of x is 2x plus 1. And a lot of times that's all you can do. Technically, the only thing you can really do to simplify what's called a rational expression when you have a fraction like this is if you're able to factor the numerator and factor the denominator, and then notice that they have a common factor that you can reduce them both by. Neither of these factors, so that's it. That's your answer. So the only other thing that they asked for on this, and this may be all that Josie wanted, so I'm sorry if you had to sit through all this, the domain of the f over g. This goes back to the questions like this that you had in module 1, where they would give you a rational expression and say state the domain. The idea was you want to make sure that you focus on the x values that do not produce 0 in the denominator. So on a problem like this, your denominator cannot equal 0. So the denominator on that problem is 2x plus 1 because the g is what's in the bottom. And you want to figure out where that cannot equal 0. All right, so we go and we solve this, we're going to get a little fraction. So 2x can't be negative 1 because I'm moving the 1 over. Divide both sides by 2. So this says the bad number is negative 1/2. I cannot have x equal to negative 1/2. If I do, then I'm going to get 2 times negative 1/2, negative 1. Negative 1 plus 1 is 0. And it's going to give me an undefined bad number, a not number, number that doesn't exist. So, sorry, not equal. So x can be literally anything else on the number line except here's 0, here's negative 1, negative 1/2. Can't be negative 1/2, but it can be literally anything else on the entire number line except for that number. That number has to be kind of pulled out of the domain. So this is a picture of what the domain would look like. Literally pick any number on the number line except for that negative 1/2. Or this is the quickest way to say it. X cannot equal negative 1/2. The most convoluted way of doing it is the way I think they want the answer in this, which is to say the set of all numbers that it can equal. So this is what we have so far. X can't be, this is the domain. This is the different ways you can say it. We figured out what the bad number is, -1/2. It can't be -1/2. We can also draw a picture that says it can't be -1/2. You can have anything else except -1/2, but that's the bad number, -1/2. Okay, but the interval notation is supposed to take like the shaded pieces on this number line and write them as intervals from the least value to the greatest value. So you've done this hopefully earlier, but if it's pointing to the left, that means all the negative numbers forever and ever. So you say that direction is -infinity. If it's pointing off to the right, that means all the positive numbers up as high as you can ever imagine, and then add another one to that. So that's +infinity. So basically everything except this. So the interval notation, we have to draw an interval for this piece. So what's the starting place for this interval? Well, it has no start. It's going on forever to the left. So -infinity, it's unlimited to the left. It does have a right-hand limit of -1/2. Okay, I just can't include it. So what I do is I put a parentheses on this side. Intervals always have some kind of grouping symbols. So whenever it's an infinity symbol, we always use parentheses because the square brackets mean that edge number is included. The parentheses means that edge number is not included, or it's not even a number, it's an idea like infinity. You can't trap that with a square bracket. All right, -1/2 specifically is not to be included, so we use a parentheses here. Most of the time in the other things, when we were doing intervals like for square roots, we would use square brackets, but not for this. Okay, the other interval, so you have to write two separate intervals. So the other one starts, the lowest value, the limiting value anyway, is -1/2. Even though I can't include it, I have to show where the interval starts. It starts just after -1/2. So I use a parentheses to say it's not included, but it's the left-hand edge. And then it's unlimited as you go up, so +infinity for the right. So these are the two intervals. This is the worst, most mathy, convoluted way of saying don't use -1/2. And then you put a U in the middle, and this means the union of all of the elements of the left interval with all of the elements of the right interval. And that's just a way, because we have parentheses around the -1/2. That's one way to indicate -1/2 is not part of any of the numbers in this set interval notation. All right, so this is what you would actually select or have to type in to get the domain question correct for that last problem, or the last part where it talks about the domain. Okay, but I think we're less concerned with if you can do this formal interval notation than if you can just identify when there's certain values you have to be careful not to plug into a function because they make it undefined. Okay, so I know that took a long time. I don't know if anybody watched all of them, if you're just scrolling through for the ones you wanted, but that is what was it, 6 problems out of the review that I had questions about. So Josie, there you go. All right, everybody else good luck studying for the test, and let me know what else you need. Bye.